All right, so we are going to be talking about hash tables today. So I'm going to start off with an analogy. So one thing to keep in mind is, remember in this class, we're always just looking at different ways that we can efficiently store data. So at this point, we know we can use arrays, we can use linked lists, we can use trees, and then we also know that there's all sorts of different abstractions we can design around those data structures. And so we're going to talk about another way to do that this week, which is the hash table. So the analogy that we're going to use is thinking about a pile of clothes. So think about the pile of clothes or the items of clothing in general as data that you need to access. So when you get dressed, you're looking for a shirt, you're looking for a particular shirt, you're looking for a pair of socks or a particular pair of socks. That's the general idea, that you're trying to access particular items of clothing or data. So everyone knows that if you want to look for an item of clothing, that if you place the items in a big pile, it's going to be harder to find a particular item than if you organize the clothes in some useful way. So if you organize by item type, like put all the socks together or put all the shirts together, then it's easier to know where to start looking, right? Now, if you don't have a lot of clothes, like, it doesn't really matter how you organize it, because there isn't really a big benefit to looking through a small pile of clothes or looking through a small pile of folded clothes. But the idea is that once you start having a large amount of clothes, that's when it's going to really matter, right? So it's going to be really hard to sort through a large pile of clothes to find what you're looking for. And it becomes really useful if you have some system to break the data up into smaller pieces. So to continue this analogy, you're going to want to think of something that we'll just call a clothes organizer. And so when you have socks come into your clothes organizer, that organizer can tell you, okay, yeah, those are going to be in the sock drawer. So it directs you to a particular location that you can then look through. Same with hoodies. They're in a cupboard. Belts, they're hanging on the door. And so instead of having to just like search randomly through, or even linearly through everything that you own, it directs you in a more useful way to a particular area. So this analogy is equivalent to, let's say that instead of organizing clothes, let's say we're just trying to organize some data that's in the form of a string. So let's say we have the string banter coming in. This would be equivalent to placing banter into bucket A. So bucket A is just like a place in memory that banter goes to. And the mapper is able to connect the word banter to its bucket. So it's basically similar to a tree that has like a key value pair. Banter is the key, and it maps to a value that is stored in a particular location. If we have a smiley face string coming in, it could map to bucket C. And if we had C++ coming in as a string, it would map to bucket D. So this idea that you can take a key and then like something somewhat magical at this point that we don't understand yet happens, and it translates it to a particular location, is basically all a hash function or a hash map is. So hashing and trees kind of do the same thing, but they do them in a completely different way. So trees are able to store data based off of some key, and it can store other things with it, like a value. So given a key, you can kind of walk through the tree and find where that key is stored in a more efficient way. Hash tables, on the other hand, work very differently. So the key comes into the hash table, and the hash table has something called a hash function that's able to translate the key into an index, and the index will tell you exactly where the data is stored for that particular key. So this hash function here is kind of where everything happens. So when you are sending in socks, it's going to tell you sock drawer. When you're sending in C++, it's going to tell you it's in bucket D, right? So it's able to translate the key into a particular location or an index. But the data structure of a hash table is nothing fancy. It's just an array. It's just a matter of getting direct access to that array via a hash function. So for a tree, when we're searching, we search the tree to find the key value pair. For hashing, we convert or hash a key into an index, and then we start searching at that index. Sometimes there's a little bit more to do than just that. And some of the trade-offs of one versus the other. So hashing is faster, and that's because this process of hashing the key to the index, or I should just square this. This process of hashing the key into an array index is an O1 process. It's like a calculation, arithmetic, that's all it is. And you do the same arithmetic or the same calculation each time you need to hash, so it's not like a bigger calculation if the array is bigger or the number is bigger, right? It's just always a calculation. So that's O1. And that's how you would insert, and that's also how you would search, and it's also how you would remove. They all just require you to hash something or run something through a hash function. So hashing is faster than using a tree. On the other hand, hash tables are going to use more memory. The reason that they're going to use more memory is because you're going to have space that's unused. So you need your array to be big enough so that there's a place for everything to go. And so you'll have places in memory that are going to be unused, unlike a tree, which is going to allocate memory each time something is inserted and connected all together. A hash table requires you to allocate space for a whole array. And that means that in a lot of cases you're not going to fill every element in the array. And so that's going to use up more memory in order to do that. And so you really want to optimize when you're using a hash table to make sure you're filling it to some capacity where it makes sense, some percentage. So how do you hash? First you need a hash function, and there's lots of different general hash functions you can use, but generally they work best if it's a custom hash function that works for the data that you're working with, and that hash function is going to hash your key to an index. And then you're going to need an array, and it needs to be the appropriate size. So that is also going to depend on your problem. So if you're dealing with a key that has more possible combinations of options, then you're going to need a bigger array in most cases. So let's check in on this. So let's say that we wanted to have the key be a UIN number, and a UIN is a 9-digit number. So instead of using a tree to store the data, what if we wanted to use an array? So if we wanted to use an array, we would need to make sure that, or let's say we wanted to make sure that we had one element in the array per possible UIN. So how big would n have to be in order to cover all possible UINs? So the answer to this is that you would need to have 1,000,000, and that's because a UIN has 9 digits. So there's 9 digits. So let's say the UIN that we're starting off with had all zeros, and let's just say that we mapped it directly to the element itself, which is 0, or the index itself, which is 0. If we did this, then at the bottom here we would have the largest UIN, which would be all 9s. And so if you added up all of those, that would be a total of 1,000,000 elements in the array. Sorry, that's not 1,000,000. That's 1 billion. So 1 billion elements in the array. So that's really big, right? So that's a lot of space compared to a tree, which would just have however many actual UINs you inserted into it. So how fast can we find the student's data given a UIN? Well, in the hash function that I just gave you, where I'm having the array be size n so that there's space for every possible UIN, and then I'm just increasing the index by 1 every time the UIN increases. So this one's going to be 0, this one's going to be... So the hash function is just like a 1-to-1. So the UIN is the index, right? It's a pretty easy hash function. In that case, that calculation is nothing. You're just going to return the UIN. But regardless of what you had to do, let's say that we modded, let's say that we divided it by 2, let's say we took one number off and added something to it. In all cases, you would do the same thing to every UIN that came in. It would be the same constant complexity, and so we can find the student's data in O1 always with the hash table, because it's just a calculation and arithmetic that you do to the key, the UIN, and it directly gives you the index, which you have direct access to the memory via an array. So when do you use hashing? Hashing works well when you know something about the data. So when you're able to understand the keys that are coming in and process them in some useful way. So in the previous example, that's not a really great data structure for a UIN, is to just map 1-to-1 the UIN to the array, because there's going to be a ton of wasted space. But you could create a really good hash function from a UIN if you take advantage of some other things about the UIN. Like, for example, there's probably a bunch of numbers that aren't used. Maybe UINs always start with some value, whatever. So when you're able to kind of customize the hash function a bit, they work really well, because they minimize the amount of memory. So UINs, net IDs, any sort of ID like that, social security number, driver's license number, vehicle identification number, all of these are typically really good uses of a hash function, because they usually have well-known patterns. So that is it about hash tables as our introduction, and now in the next couple videos we're going to go much deeper into how to write hash functions.